All right, so now it's recording. What was your lab apparatus again? Yeah. Remember that?
It was a hanging mat, and then a pulley, and then a car on a track.
Yeah, so you guys see how this is a pulley? See my nice pulley right there? And then I got an object hanging. Is everybody good here? Yeah. And then I've got another object right there. And in our lab, we had a cart that simulated a block with almost zero friction. But you guys actually know how to deal with friction now. So maybe in a problem like this, you would know M1, M2. You might know mu, and we'll call this mu k. Are you guys with me? And we'll say the system is sliding. Do you have any idea which way the acceleration is most likely in this case? For M1? I don't hear you guys. Please join along. I think some of these strategies will actually help you a lot. When you sketch a diagram first thing, right? Every problem? Yes, we sketch diagrams every time, every problem. Not force diagram. I mean like a diagram of the situation. And on that diagram, show which way the acceleration vector is. It's extremely important because you may never do a correct vector sum diagram if you don't think about which way the acceleration is. Am I right? Yeah. And you'll get it wrong. It'll be a disaster. All right. So everybody's good so far, right? M2 is going to have an acceleration down, M1 to the right. So this makes the force diagrams very easy. Why don't you tell me what the force diagram for M1 is? Help me. Weight. What else? Okay, normal. Okay, normal. Weight. Hey, one trick that's actually extremely important in problems like these, God, I hope you guys don't miss this, is this little trick there. Because then when I start to algebraically solve for stuff, I'm not likely to mix up weight of object 1 with weight of object 2, which are not the same. You with me? I've seen a lot of people struggle with that. So your symbols, having clean, beautiful symbols, really can make a difference. Just being kind of methodical about it. And which way is the tension? To the right? How would the tension to the right compare with the friction to the left? Would you, if you saw mu k, would you think there's friction to the left on M1? Yeah. How much friction to the left? Please help me. Less. Why less? I love your logic. Good. So I'm going to label that kinetic friction because it's sliding. You guys good? What would your next step be with that system? System M1. That's what this is. All right. And when we did the lab, you didn't know everything you know now. Okay? So it was simpler for us to have M1 and M2 all one system. Are you guys good? All together. That was much more simple. Read the name, meet a friend.
Steve.
Steve Cicillo?
Yeah.
Okay. If we make M1 and M2 our system, it's pretty easy to see that the acceleration is going to be the total mass, right? It's going to be related to total mass and the net force. Are you guys with me? The only force not balanced by anything else is the weight of object 2, right? Everybody's good? Now, we pretended there was no friction. Can you see how now it's much more complicated? Our little tricks might not work as well. You guys get what I'm saying? So, I'm going to show you a different way of doing it. Good luck on your test tomorrow. Try to watch the screencast. So what would you do next with your system 1? I forgot. Vector sum diagram? All right. And so I'll do that right here. Tension. Weight, I'll call mg. And then friction, super short. And then I guess I'll draw normal right there. You guys liking it? Normal, tension, mg. Okay, I'm sloppy. How can I make it better? Look at mg. How do I make it better? Huh? Good. Because when I do my vector sum diagram for the other system, and if I'm not careful with my symbols, I will confuse the two. Right? I don't have numbers here. I'll get all mixed up. So be clean with your symbols. Okay, I'll shut up. What's friction again? So from your reference sheet, you know weight equals mg. You know friction kinetic is equal to mu normal. Am I right? You know Newton's second law, net force is ma. It's written in a different form on your reference sheet, and weight is called Fg, but it's the same thing, right? Is everybody good? Okay, so my acceleration is this way. I'll make a ma vector, and I'll call this other one, I'll call it mu normal. I like making my ma vector a different color. Are you guys good?
Yes, sir.
Okay. Can y'all tell me the force diagram for system 2? All right, and weight down, tension up, and they're the same length, right? They're not the same length? Something's wrong. They're not the same length? How sure are you that they're not the same length? 100%? Half?
100%.
Why then?
For that one, right?
Yeah.
You drew it so that it's not the same.
Do you see how important it is that you write A and show the direction of your acceleration next to your system? So you don't forget these huge ideas? I think I rarely see people when they write A down and they label it next to their diagram, it's like a reminder when you're doing your force diagram that your weight of system 2 must be larger than what? Are you guys digging? It all comes together when you're methodical like that. And then you got weight 2, so that's m2g. You got tension up. Are you guys liking this? Tension up. There's a few really difficult things here that people struggle with. First thing, is there anything that unifies? Oh, how's this for sloppy? M what? Okay, that'll keep me from getting confused right there. Now, I got a question for you guys. Let's just hypothetically say M1, we know is different than M2. They're not the same mass. Is the net force vector going to be the same? Let me go back a step. Is the acceleration of both of these systems going to be the same? They're connected by a rope. It has to be the same acceleration. Is the tension in that rope going to be the same? So the tensions, what I'm trying to get across is this tension and that tension are identical. They have to be. Same rope. All the pulley does is change the direction of a force. That's it. But if they're different masses, do they both have the same exact acceleration because they're connected? The acceleration of that entire system of objects is identical. So you can unify the equations either with tension force, which is the same. In other words, I solve system M2 for tension and plug that into the other system's tension. Do you guys get what I'm saying? I could potentially solve for 2 unknown variables because I have 2 equations. One from system 2, one from system 1. And acceleration's the same for both systems. Tension is the same for both systems. But I want to highlight, is net force the same? Is the MA vector the same? Look, A is the same for both systems.
Yeah.
A is the same number. But is M the same?
No.
This vector, if this mass is bigger, that vector bigger. If this mass is bigger, that net force vector is bigger. Even if A is the same. You guys good?
Yes, sir.
Anyway, I hope that helps. Right now in class, I want you to finish this problem and find this acceleration of the system in terms of the other variables go. Let me see if that works. Yeah, I'm just going further now. First, I'm going to label this little M1 that I've neglected. Are you guys good?
Yeah.
So, appreciate it's really quiet. Kind of recording right now. So, I'll say tension from my system M1. Tension is M1A plus mu normal. Are you guys following?
Yeah.
And you probably all got that. M1A plus mu normal. And I can go further. Tension is M1A plus, notice I see that normal is M1G. Do you see where I got that? Right here from my vector sum diagram?
Yeah.
So plus mu M1G. Are you guys happy?
Yes.
So now I have a nice, from system 1, I have a nice relationship for tension. And I know the tension is the same that acts on system 2. You guys good? And so from system 2, I can see from my vector sum diagram that tension is going to be M2G, right? Minus M2A. You see how I get that out of my vector sum diagram? Do you guys all see that? I mean, I literally look at the vectors and I'm making an equation out of the relationships I see with the lengths of the vectors. I could have written M2G is T is equal to T plus M2A. It's the same thing. You guys good? But I knew I wanted T. Actually, yeah. So, do you see how I can unify these?
Yes, sir.
This must equal that.
Yes, sir.
So, maybe I'll do that in the middle to be cute. In a different color.
Oh.
All right? M1A plus mu. That's a mu K, right?
Yeah.
Mu K M1G equals M2G minus M2A. Is everybody happy?
Yes, sir.
And it's like world of algebra, but it should make sense in the physical world when we're done. I see, what am I trying to find here? Help, please. What am I looking for? What did I say to solve for? Okay, I said I'd like to know the acceleration, right? In terms of all the other variables. Well, all the other variables are just going to be M1, M2, and G. I have two terms with A in it, right?
Yes.
So let's rearrange those terms together. M1A
Plus M2.
plus M2A. Yeah.
Equals M2G minus mu K.
Could you say that a little louder, please, my brother?
M2G minus mu K M1.
You guys liking? If you're methodical about it, you're going to get this one perfect, I bet. So what do I do next? I want to solve for A, right? This is algebra.
Take the A out.
So factor out an A. What you get there?
A times M2 M1 plus M2.
You feel free to stop us if we're losing anybody. So I got M2G minus mu K M1G. You can see how this problem would be worse if there was an angle on the track. It would be a lot worse. Well, I don't think we're ready for that right now.
Yes, sir.
But it could go there one day.
I hope so.
Well, it's more real life.
I know so.
Are you folks good with the algebra? We're playing algebra games now. So A is like that, right? Now, I really do love this part of physics because I can test my equation. I can first look at units and I can be like, well, what units am I talking about? A better be meters per second squared, right?
Yeah.
Well, I know G has the same units as A, and I got meters per second squared over kilograms. Something's wrong. Oh no, I don't. I got kilograms times meter per second squared for my first term,
Yeah.
m2g. That's kilograms times meter per second squared divided by the kilograms in the bottom. I'm good.
Meters per second squared.
We're going to get acceleration. And then the same with my other term, my mu k m. So the units work. That doesn't mean it's correct. That just means it might be correct. Okay? So there isn't something silly wrong, which happens. So it's a nice first check. The second check I like, oh wait, I can make that look prettier. I just realized it. Did you see that? Factor out what?
G.
Then it'll be easier to make sense of m2 minus
Mu km.
mu km.
1.
Are you guys with me?
Yes. Over m1 over m.
That's beautiful, huh?
Yes, sir.
Now, check it out. Notice if m1 goes up, does acceleration go up or down? What should happen if we increase m1 by logic?
Acceleration should go up. Or down, go down.
Imagine you have a net force applied to an object and that object gets more and more massive. That's what's happening with m1, right? If m1 gets more and more massive, doesn't the acceleration go down, right? So it makes sense that if I increase m1, I'm increasing my denominator, which decreases the acceleration, and I'm subtracting in the numerator. So m1 will serve to decrease my acceleration when it increases. You guys like it? And that totally makes sense. What about m2? That should increase the acceleration when it increases. And when I look at m2, well, it's true it's in the denominator, so it doesn't seem that's not a good sign, but that's okay. All good. It's also in that first term. And in the denominator it's added with m1, so it doesn't have as large of an effect, right?
Yeah.
So the bigger effect is going to be the term m2g.
Multiply.
It's as m2 increases, it does seem like your acceleration will increase. You like it? What if the surface became rougher? Mu k would do what? If mu k went up, does that decrease our acceleration?
Yes.
Now, does that make sense?
Yes.
So using your imagination to play with the variables and imagine what happens is the way we check our stuff. Are you guys good? I think that's about it. I hope this helps. Do you have any questions before I shut this off?
On our test.
Speak loud.
On our test, is it gonna be like this? There's not gonna be any numbers.
Well, on the test, I'll never, ever do the same thing I do in class.
Yeah.
So you won't see this exact example. But the same skills, the same types of things are highly likely. Bent around in a different way. If I can tweak this, if I can change the scenario to something different, but you're still basically doing the same thing,
Yeah.
that's a true test of your understanding. Because you're applying what you learned to a new situation, and to me that shows you really understand something. It's hard, I admit. But that's why AP Physics is hard. You're applying what you learned to new situations. That's the true test. Are you guys good?
Yes.
Anything else? All right. Did I even answer your question?
Yeah.
Okay. Cool.